All right, so we're going to look at a situation where you've got an integral and both the powers are even. So you have something like this, sine m to the x cos n to the x dx with even powers. So if both m and n are even, what we're going to do is we're going to use these identities. So yeah, let's have a look at the identities that we'll need. These are the power reduction identities, which I actually don't think I made a video on, but I'm sure I will at some stage. But basically, if you've got sin²x, then that's equal to a half 1 minus cos of 2x. And so this is something we're going to need in order to solve problems of the form shown above. So let's have a look, or we can use this one, which is our double angle identity, which I'll put a link to below to explain why that's the case. So sine of 2x equals 2 sine x cos x. And we're going to need to use that a little bit as well. Another thing you need when using these, trying to solve these problems, is this situation, that the integral of sec² kx dx is 1 on k tan kx plus c, and also this 1 plus tan squared x equals sec² x. Because yeah, we're talking about even powers. So that's sort of just our little cheat sheet we're going to need in terms of things we might need to solve problems. So what we're going to do now is we're going to do an example, and we'll just do the example where we get sin²x cos²x dx, and our job is to find the antiderivative of that, so that yeah, we might be able to find definite integrals of that function, and then we'll look at a picture. So just given the fact that we've been given these identities already, hopefully you can see what a good first step might be. We can see that the first part of the integral there is sin²x. So yeah, if we're going to replace that with a half multiplied by 1 minus cos of 2x, we'll get this, and I should explain. So the cos²x part of the integral becomes 1 half 1 plus, I should say 1 half multiplied by 1 plus cos²x. And then we get the half in both situations, so it becomes a quarter out the very front. And then I encourage you to think about what we might be able to do from here. But 1 minus cos of 2x multiplied by 1 plus cos of 2x should sound quite factorizable as a difference of perfect squares. So hopefully you would agree that we could do this. We can take the quarter out the front, and then we can say would it be 1 minus cos² 2x. Okay, now this is where we need to know our Pythagorean identity. Again, I'll put a link below for that, but 1 minus cos² 2x is the same thing as sin² 2x. So we get a quarter sin², the integral of sin² 2x dx. And then what we can do, and this I think is the trickiest part, we're going to use basically this first identity again. We're going to use this one here, but we can see that it's sin² 2x. But that just means this is going to become a 4. Because if you just imagine, you make a substitution where x is equal to like 2 theta, then that just gets carried into here. And so this is going to become 4. So if we show those steps, it becomes like this. So we get a quarter, the integral of 1 minus cos of 4x on 2 dx. Yeah, which is just the fact that we've got a 2x here now instead of just a regular x. So that becomes a 4x. Okay. And then you get 1/8 the integral 1 minus cos of 4x dx, because you factor out the 1/2, and there's a quarter there. So half times a quarter is 1/8. And finally, this is something that's actually quite integratable, or we can find the antiderivative of this hopefully straightforwardly. When you antidifferentiate a constant term, it becomes x. So this is going to be x minus, let me just show you, sine of 4x on 4. When you integrate negative cos, you get negative sine, and you divide by 1 over the coefficient of x. So you get this situation. And there's our answer. We've been able to work it out. So let's look at a picture, because that's all very algebraic and not much fun. So let's have a look at what a picture looks like. Here's our axes, and here's our function. So that's our function sin²x cos 2x. if we take the area over 0 to pi, we get approximately 0.39. So I encourage you to go to your CAS or use Desmos or something like that to check that that works, but pi is here, right? This is pi. And so from before, we just found an antiderivative, didn't we? So our antiderivative was this, 1/8 x minus sine 4x on 4. And so what we should know from the fundamental theorem of calculus, hopefully, is that if we're just taking integrals from 0 up to some point, then the antiderivative will find the accumulated signed area between 0 and that point. So I suppose what I'm getting at is, at the x value of pi on this pink line now, which is the antiderivative of our original function, we should get 0.39. And sure enough, that's the case. It gets a bit trickier when you're taking definite integrals between different values. But yeah, if we're just doing it from 0 up to some point, then we know that the antiderivative calculates the accumulated signed area. So, and it's all positive here. So hopefully you found that interesting. If you did, give us a like. If you need any private tutoring, let me know. And good luck with all your studies. I'll see you soon.